how streaming data pipelines today work and how they are different from batch. What are some frameworks to think about when we think about streaming at scale? Um, just a little bit of introduction. I'm a data engineer with CVS. Worked on big data technology across different stacks and different cloud providers. Currently working on cloud data modernization under PDM. And hobbies are just like data engineering, horror movies, and my dogs. So that's about me. Um, so the agenda of today's talk is basically to talk about some key terms, and I'm specific about those key terms because a lot of them we don't use in our day-to-day lives in batch, which is a much more common paradigm when it comes to data processing. So I would like for us to go over those. And if you guys also have your experiences, please feel free to share. And then talk about design thinking for a real time pipeline. What are some common issues that we face? And what are some options or thinking strategies to solve those? And then we can probably interact more. So some of the key terms that are used in streaming, which are a little different from when we think about batch, is firstly the fact that stream set is an unbounded data set. When we say bounds, we talk about the limits or we talk about the boundaries of the data set, right? So let's say there are some files, or let's say there is a warehouse in which there is data. If you're processing it at batch, you know that, okay, this file starts here, it ends here. So there are definite set boundaries to that file. Whereas in streaming, there are no bounds. When a stream set starts, there is no stopping it unless there is a network issue, a bandwidth issue, or there is a failure on processing or something happens. In a normalcy or in a normal condition, a stream doesn't just stop. So that's why we call a stream set as an unbounded data set. Lambda architecture, this is, have come across this term a lot more now than I used to before. It's just that streaming execution happens with the batch execution. So there is an architecture where both coexist in a way. Then are some more important terms: event times, processing times, and windowing. So event time is a timestamp that is attached to the event when it's actually happening. Basically, when it comes to things like Kafka, PubSub, or any of those messaging systems, usually they have an event time attached to it. So let's assume we are playing a game and I click a button. I like Mortal Kombat a lot, so maybe I'll give that example. So if I'm putting a blow on someone and it's fatality or brutality or whatever it is, all those clicks uh, from my console are going to the server, right? All those clicks have an event timestamp attached to them. And we see that in fruition when we look at those events in a streaming service or in a, I would say, streaming sync or whatever you want to call it, a messaging service like Kafka and stuff like that. So that's the actual true time captured by the system when the event is happening, which can be same or materialistically different from the processing time when we are actually processing that data. Now, if for example, I've sent a message to someone on WhatsApp, I'm using WebSockets protocol to send the message to someone. And for some reason, my mobile data network goes, or their data, the receiver is not turned on WhatsApp or something like that. I have still sent the message at 10 a.m. But when they receive it and they process it, depends on a lot of things, right? Their bandwidth, when they are processing it, how much time they are taking, etc. So processing is when you're actually acting on that data. An event is when that data actually occurred. And these two make streaming much more complicated than they do batch, because in batch you already know, okay, this is my bounded data set. I have gotten it. I will process it using a batch pipeline. Now, if it's trigger based batch type pipeline or it's like a scheduled batch pipeline, you know, basically that I'm going to process it within these finite bounds of time. Whereas these two terms make a difference because of this graph here, which adds skew. Basically, now delays start happening in real time streaming pipelines because there is a miss or there is a discrepancy between when the data processes versus when the data happens. That makes batch much more complicated than streaming. And that's why I wanted to keep those terms here. The last term is windowing. So I assume all of you might have worked on group buys or trying to group some data or bucket some data and perform some aggregations on that data in the batch world. If it's SQL, we do group by. If it's PySpark, we do group by in the Spark SQL, etc. Now, there can be situations where we would want to do the similar group by on streams as well. For example, if I am playing a game for 10 minutes, I might want to know my score after 10 minutes or something like that. That means that there needs to be an SDK, a software, and the infrastructure to support accumulation of my data for a finite time, even though the data is unbounded. That's windowing. We are windowing the data, the streaming data, into finite windows so that we can aggregate them. Why do we need this concept when it comes to streaming? You can't aggregate what's unbounded. How will you know when to stop? Like math needs finite computations. You need boundaries and limits to everything, even if it's streaming, right? In case of aggregations, in case of other calculations, like for example, if we are doing filtering, you don't need windowing. You will filter whatever is coming in your way, apply the filtering logic to it, and it keeps getting filtered as it's coming. But if it's aggregation, you need windowing. So that's why I wanted to add that to this slide, that that's also a very key term that we basically use. And windowing married with event and processing timestamps sort of form the crux of how we think about the software development of a streaming pipeline, because these three concepts have various different constructs which help us take decisions, and I'm going to talk about those decisions very soon. But these are some key terms. And again, this is just a pictorial representation of what I got it from Tyler Akadau. He was one of the senior devs at Google who wrote the data flow paper, and he wrote the book as well, the streaming, very popular. So he tries to explain what is a bound, what is unbounded data set, and then what's filtering here. So the difference between the figure 2 and figure 3 here is, as I was mentioning, streaming, if you're filtering something, you don't need bounds. You filter whatever is coming your way, it gets filtered, and then you process it later. You need bounds to streaming when you want to aggregate things, or you want to process things in finite windows and throw results out. So that's why you need this all this concept here. So basically, this is where streaming becomes extremely tricky and very interesting and very beautiful as well at the same time, because of network, because of any delays between the various points of integration in streaming, and the points of integration can include the application that is writing data to PubSub, for example, or PubSub pushing the data into a processing engine, or that processing engine pushing the data further down into a data lake or a delta lake or wherever the storage is. There usually is always some discrepancy between processing time and event time. Your event might have occurred at 9 a.m., but it is appearing in your windows at 10 a.m. or at your wall clock time at 10 a.m. or 11 a.m. That's where it becomes extremely imperative to understand the concepts of windowing, event time, and processing time very clearly, because that way you will know that, okay, I do have scenarios where I have late arriving data and I do need to process it somehow, or I do need to deal with it somehow. So that's why this figure basically shows here that, so basically something came at something that happened at 8 a.m. is coming in my 10 a.m. window. Now, do I group by on it? Would it give me wrong results? Should I ignore it because it's already late? What do I do? Just understanding this takes a lot of thorough analysis, and I'll show you some ways in which this can be mitigated, or this can ease out a little bit using Apache Beam. But just wanted to show you that one of the biggest complexities in streaming is that there is no guarantee when the data events would appear with respect to when they occurred in most of the practical streaming pipelines. If there is absolute perfection, then good. Like then that actually means, okay, I am going to process the data whenever it comes. I don't care if it's late. I don't care if it's in order and stuff. And mostly my data is never late. If those are the kind of things, then streaming becomes almost as simple as batch because everything is predictable. But when practically we look at internet and the world of internet and the world of cloud, where a lot of things are out of our control, and in my opinion, it's not even prudent to control bandwidth which travels across the oceans. Now there are ocean networks. What we can do is we can mitigate and acknowledge the fact that the data will come late, the data will have discrepancy between event time and processing time, and take measures to sort of solve it in our pipelines. So that's why this figure basically shows how data can appear late anytime, and we will have to decide whether we process it in the window it is coming, or ignore it, or do something else. And I'll talk about that something else very shortly. So there are two things, right? Like I think I prematurely covered these things when I was talking, but I'll still emphasize on these: correctness and completeness, right? Let's talk about batch first so that we can sort of draw parallels and juxtapose those concepts with streaming. In batch, what's correctness? The correctness is basically whatever is there in a file or a table in a warehouse or a table in a database, and all of that should be processed in accordance with the business logic, and we write our unit test cases, do our regression, reconciliation tests, and all. That's correctness in the world of batch. What's completeness? I should process the full file. I shouldn't process only 15 records out of 1,000 records in a batch file and stuff like that, right? Now, let's take these concepts to streaming. In streaming, correctness stems out of the fact that how your event time and processing time are behaving with each other. That makes it correct. Why? If I go back to the previous slide, if the data that happened at 8 a.m. is coming at 10 a.m., you might be putting it into a wrong window when you're doing group buys, and you might be computing wrong results. For example, you might be computing incorrect game scores for your past game if those game scores are coming in your previous current game. That's the correctness here in streaming. Completeness. How would you determine whether you've analyzed all the data for a given event time? That's completeness. So and I'm emphasizing on these because the next topic that we are going to talk about is watermark. That's the bible for streaming, and that governs everything else that we talk about. So correctness is one, and completeness is, are we confident enough, or are we confident to a certain degree on that? Okay, for 8 a.m. events, I am okay. I have processed most of those events and I'm good with it. And I want to now start processing the 9 a.m. events or 8:30 a.m. events. That's completeness in the world of streaming. Very different from how batch works. And that's why I wanted to emphasize. And there is always a dilemma between, hey, how do I fulfill correctness? How do I fulfill completeness? And there are some software development practices that help us understand or address these. The first one is watermark. Watermark is nothing but the notion of completeness. Whether I have processed 90% of my events for 9 a.m. event time, And again, I'm emphasizing the word event time because event time and clock time are very different. My event would have happened at 9 a.m., but it's already 10:35 a.m. now. So am I processing all the data that I had for a given event? There is absolutely no practical way to know unless someone has business knowledge or someone has like inside out knowledge of their tech stack. Still, a data can come late. That's what the point is. So watermark is nothing but it's the notion of basically uh, whether the data that you've processed for a given event time in the processing time window has been complete or not. Trigger. Trigger is the magic word. Trigger means what do you do and when do you do when the watermark is complete? Basically, do you want to throw results into another data structure in memory? Do you want to do some aggregation? Do you want to do summation? Whatever. Watermark is the implementer. Sorry, trigger is the implementer of what watermark tells it. So watermark tells it, hey, I am done. These are the events. You need to process all these events now for 9 a.m. event time. I am not going to process any more events for 9 a.m. if they come late. And trigger will be like, okay, I got it, watermark. What do I need to do? The code will say, okay, trigger results, send them to BigQuery, for example, send them to a file, persist them somewhere else, or send them to somewhere else. And then comes accumulation. So do you want to accumulate your game scores within those 10 minutes, or do you want to take the latest one? Do you want to discard everything else? Accumulation has to do with the state. And the moment we use the word state here, our pipelines start becoming expensive because we need to store the state somewhere. So those are the three concepts. If we talk about the level of importance, I think watermark and trigger are more important because one is like basically what's my absolute threshold to start processing, and one is what do I process or how do I process it. So those are the two important concepts here, and bringing all these concepts all together. So what are the transformations I'm doing, right? I'm doing filtering, I'm doing group buys, I'm doing like any kind of aggregations, training ML models. What is my business goal or what is my technical goal to write this pipeline? That needs to come with talking to business or talking to the tech team. Where in the event time are the results calculated? You do the windowing here, you do event time windowing where you divide the data into shards, right? Windowing is nothing but the sharding for windowing is nothing but what sharding is to batch or partitioning. That's one of the widely used terms for that. When in the processing time are the results materialized? We just spoke about it, which is the combination of watermarking, which tells when I need to complete the work, and triggering, which tells, okay, what do I do after the watermark is achieved? And how do the refinements of results accumulate? Okay, I got 5 game scores for a particular player in this event time, in this window, and trigger is asking me to push those results somewhere. Do I accumulate all those 5 or do I take the max or do I take the latest? What do I do? So these are all the concepts. And there is so much focus on these concepts because these, at least in my experience, I haven't thought through or spoken about these concepts to anyone when we design batch pipelines at scale. Like in batch, the most important things that we deal with day to day are, oh, the data is skewed. Oh, my cluster is not running because the performance is slow or something like that. Or, oh, my backfilling pipeline is not working because something is not working, or my data quality is not that great because of XYZ factors and all. In streaming, yes, you can have all those issues, but these are the more common and the more complicated ones. Oh, my data arrived 1 hour late. It's business critical. Do I process it or do I ignore it? Because if I start accumulating the data for 1 hour, I'm adding a lot of RAM and a lot of disk space to my streaming pipeline now. What do I do? Should I optimize what the business is asking me, or should I bring my cloud costs down? What do I do? So streaming has completely different kind of issues, plus all the issues that batch has. Now, How do we handle late arrivals? Basically, this was a question that I used to always have in my mind when I used to think about streaming or read about its theory or even work on it a little bit back. One is the easy way out, which is you keep the state of the data infinite. You don't lose that data. You have windows, window one that is for event timestamp 9 a.m. to 10 a.m., window 2 that's 10 a.m. to 11 a.m., etc., etc. Now, even if the data comes late, okay, I'll process it whenever it comes. But for that, you are persisting those windows forever in your memory. How much money will you have to process all that? Or how much disk space will you have? Or how much RAM will you have? First of all, it will burn your pocket. Second of all, your cluster will run out of memory at some time because you're storing all those windows because you want to process whenever whatever comes at what time. So it's uncomfortable to admit it from my side, but it's still practical to have practical boundaries around lateness. Okay, if the data comes 15 minutes after my watermark, I'm going to process it. If it comes after that, I'm going to discard it. Those limits are something that a lot of big companies who use large scale streaming use these days, because otherwise you can't store the data state infinitely. That's imprudent to do so. And how do you do that? You do that using triggers. Triggers are the way you can allow lateness up to certain time after a window has completed in Apache Beam. And I also added a programmatic example here where if you see there is with allow lateness duration standard minutes one. So one till 1 minute after your window is done, you can allow events in that window and they will come and you can process the data. That's how you can basically do it programmatically. Now, this is just the piece of code, right? What are the implications of this? This means you need your memory for 1 more minute for every window, right? Which means you need more memory in general. But that's still okay if you know that your pipeline will have late data for sure. It's always good to have this uh, strategy in mind. But what this also means is that any data that comes after this trigger happens, it will be dropped because you've already defined that, hey, I want the data to be processed after 1 minute in this example, for example, after the window, after the watermark has achieved. So this is how you handle late arrivals using triggers. And that's why triggers are very, very important in the world of streaming. Backfilling. Um, when I started working on streaming, I used to think of backfilling as a negative word because I used to feel, because again, I was so, I would say, institutionalized with the idea of backfilling in batch that I would think, okay, backfilling is done when something has failed for me. And I need to backfill, or there are data misses because of something, something, something. That's applicable to streaming as well. But imagine one scenario where you have to recompute something on streaming data with a different code base. For example, let's take example of Google Ads or something like that, where you have some ads, you have some impressions and something, and you were detecting some fraud on that, for example, using streaming. And now you have 3 years worth of that data, but you're like, okay, I don't think I did it too well. I want to use a different algorithm to see whether that algorithm works better on that fraud or not. If you do it on the new stream, you'll not be able to compare your algos, right? Because you'll have brand new data and stuff like that. So you'll be like, okay, let me do it on the last 3 years of data that I already did my previous fraud detection on and stuff. That's a classic example of backfilling where there's nothing wrong in this world, but you still need to backfill. You're using 3 years worth of data. Now, how you backfill, I'll come to that. But you're using 3 years worth of data and replaying all that data and then running a fraud detection algorithm, the new one on that again. So why do you need backfill? You need backfill for some upstream data changes, something happened, some schema or something, source sync failures, dependent system failures, and an example that I told you where you're trying to refactor something and you want to do some regression testing on what was the old code, old data, what's the new code on the old data, so that you can compare both, right? One of the easiest ways to do the backfilling is storing the state of streams in your messaging queues or in your PubSub or Kafka, and both of them have the capacity to persist the state of your streams and you can replay them. You can be like, okay, let me checkpoint the data for 3 months, basically, and I'll replay the streams from this time to this time for 3 months. That's the easiest, simplest way to do backfilling, and cloud data platforms provide that capability with the kind of messaging queues they provide. So software development wise, there is very little complexity to this. But this again becomes expensive from an infrastructure cost standpoint because now you're paying extra money to save the state of your streams in your messaging queues. The other approach is a little more interesting to me when I was reading about it, which is you basically use data lakes for batch processing and backfilling. You convert backfilling into a batch processing because in the example that I was talking about, where I wanted to apply my fraud algorithm on 3 years worth of data, if I had it in a data lake and I processed it, I would still get the results, right? So based on your business application and based on your needs, if you want, you can always store the events in a data lake and then process them as batch. Here you have converted backfilling into batch processing while still keeping the normal business as usual stream processing alive. So here is where the concepts of batch and streaming start converging if you want to save some money and if you're okay with batch processing. So this is what backfilling is. And now I also want to talk about, I think we spoke a lot about the software part of it on what's trigger, how do you implement a trigger, what's late arrival, how do you do backfilling and stuff. There are a lot of infrastructure related challenges at scale which come with streaming. Like if Twitter is processing a billion of events every day, or Netflix is doing a billion of or trillions of events where users are clicking, looking at things. Netflix is uh, giving out data, streaming data, etc., etc. That infrastructure is another science to manage at scale, and there are so many small and big issues that come with it that it's imperative to understand how you manage the infra. Auto scaling is a very widely used term, but I'll come to the reason on why I used it here. I think all of us have heard about horizontal auto scaling, right? Like, okay, if my Spark cluster is in batch, I'm talking about the batch world. If my Spark cluster is slow, I don't want to optimize it. It's already optimized. Let me throw more compute, more memory, and add more worker nodes to it. If there were 5, let me do it 8. Let me do it 10. Let me do it 12 and stuff like that. Or stop the job, have a new cluster that has more RAM, more memory, do vertical auto scale, do vertical scaling, not auto scaling, do vertical scaling and rerun your job. In streaming, we can't stop our jobs. It's a stream. It's already started. We can't tell a user, oh, at Netflix, can you please wait for 1 minute? My stream is restarting on a different cluster. I'll send you the movie in a minute. Like, just stop on this action scene and I'll come back to you. James Bond will be back in 1 minute because I'm scaling vertically or something like that. You need all this to be happening while the pipeline is running. This all has to happen when the data is in motion, when the processing is happening, when uh, when the jobs are in flight. Now it's still easier to think about it from a horizontal auto scaling. Okay, I'm probably my CPU and my RAM are continuously giving me logs where they're showing my memory is hitting 90%, 95% and all. Let me add more such machines. Let me keep adding them. Let me keep adding them. What if that's not working? What if we genuinely need more compute for some aggregations and less compute for some aggregations, and we need a varied cluster which has machines X for something and machine Y for something? That's where vertical autoscaling comes into the picture. It's a very different concept than horizontal autoscaling. Google Cloud Dataflow is one of the services which provides vertical autoscaling. How do you do vertical autoscaling? So let's assume we have a job. That job does 3 steps. It filters, it aggregates, and then it writes the data somewhere in a data lake or something. For filtering, for example, you need to pass all the data. No accumulation, no windowing, because whatever is coming now. But it's still basically you're windowing, sorry, you're filtering, so you need memory. And also you say that, okay, let me give this 16 GB RAM per machine, and I have 5 such machines and stuff. Okay, filtering is sorted. Everything is going great now. Now the windowing logic comes. You are grouping by or summing the data in streams. You have applied triggers. You have a late arrival. You have everything happening, every cool software that's happening. And that's somehow not working on the 16 GB worker nodes that you have. You have 5, you have 10, you have 15. Why? There are keys there that need to be accumulated in one machine itself to do the processing. That's where you can define hints in data flow, and those type hints can tell you, hey, for this windowing and aggregation, I will need to use a 32 GB RAM machine. So whenever I'm doing that windowing and aggregation, vertically auto scale my cluster, and then you can bring it back again. All this is happening dynamically when the job is running. That's how atypical streaming is from batch, basically. At least in my experience, I have seen a lot of auto scaling with cloud services like EMR, Dataproc, Legacy Spark, Databricks for that as well. Whatever the services are in there, they do horizontal auto scaling. Vertical auto scaling is a unique concept, and I've seen that with Dataflow with those type hints there. Dataflow Prime does that. Dynamic work rebalancing, very, very important, extremely important concept from an infrastructure management. We all have heard of the word skew, right? There is skewness in data. I don't think there is perfect data. If we are having data by states, every state in United States is different size, different population. Real estate, for example, my favorite topic. Some states are actually very expensive. They have more houses, less demand. Some states have a lot less houses, more demand and stuff. This is natural skewness, right? Entropy in the data. It is bound to happen. This skewness our pipelines don't like, basically, because the VMs are very, or the compute that we throw at the VM, the batch and streaming pipelines, they are very agnostic. They are like, okay, I have 16 GB RAM or whatever RAM I have. If I allocate 8 GB or 50, 60% efficiently to whatever work, whatever I can do in that, I'll do. They don't care whether they're processing California's data or they're processing Washington's data. What happens when they start caring is when one data is materialistically larger or starkly larger than the other data set. Then they're like, oh, now what do I do? My capacity is limited. The data is not. So skewness comes. We do partitioning, we do manual partitioning, we do sharding. There are business and database analysts sitting for hours and hours to determine that logic. And then again, data changes. Again, the shard keys, again, they start getting skewed. Then we divide those shards into other shards. Okay, in Washington also, let's do this county and this county as shards. Endless process there. We need something that can dynamically balance the workload without being predictive about it. In all these examples that I gave you right now, let's go to the map reduced time. 2009, 8, 10, I think. Though that was the time I was still in college. Mappers used to be predetermined based on how many you had, how many partitions and all. In Spark also, you tell them, okay, I need a 128 GB partition for input reads and all that stuff. You are telling things way in advance. Yes, I respect the fact that we have already done a lot of analysis on the data, the Spark developer or the developer, and they know how the keys are, how everything is. Still, things can fail. Still, the pipelines can be skewed at some point. Still, there will be one or two joins that will be a pain because there will be something in the data that would irritate. So, how do we not take this tension? Focus on the business logic, focus on what our streaming needs to provide to the business, and have the infrastructure manage it for us. This is done using dynamic work balancing. What dynamic work balancing means is you forget the concept of having fixed partitions from the very starting. You rebalance your workloads as you're progressing. So, for example, you gave 5 partitions to a data set in the very beginning. Okay, it didn't work out. I'm just left with 5 minutes. Wow. Sorry. I'll rush it. I was just thinking I'm talking too fast. Sorry. Um, so there are just 5 partitions basically that we have there. Now, if that doesn't work out, okay, we can have various paradigms that can tell us compute and memory while the jobs are running. You can say, oh, I need 10. Let's do it 10 when the job is in the flight. What are you doing? You're dynamically balancing the workload when the jobs are still running. Dataflow does that. Cloud Dataflow provides that dynamic work rebalancing. You don't have to worry about it. And I'll show a slide as well of that. Shuffle engine for batch. Shuffling is one of the most theoretically and practically, shuffling is one of the most expensive operations in batch processing. It's always good to have the shuffle state separate from the streaming state. And the same thing with streaming. Keep your windowing separate from your worker nodes. Keep them in a backend infrastructure that's separate. It will save a lot of hassle of auto scaling, upscaling, downscaling, etc. All these things are provided by Cloud Dataflow Prime today. So I just wanted to say that these challenges solving manually are not easy. You need a service that can do it for you so you can focus on your code and your business logic. This is what I was talking about with the dynamic work rebalancing, where you see there is predicted completion for 2 of those stragglers. We call them stragglers because they're straggling. And they are the late ones compared with the other ones. And with the dynamic work rebalancing, I'm allocating some of their work to the worker nodes that have already completed their work. So I'm like, okay, hey, teammate, if your teammate needs help, just take some of their work because you've already completed your work. You're dynamically balancing the work when the pipeline is still in motion. How beautiful is that? So that's what it is, basically. And I think the last session that we had, it had a lot of out of memory issues. So I wanted to cover some of this as well. You'll still have OOM issues. Basically, there will be some workloads here and there that would still have OOMs. So we can always first optimize the code, for example. That's the best way to do it. But if that doesn't happen, then you just throw more compute or reduce the number of threads in your machine so that you have more memory per thread. I'm saying this not because it's easy. I'm saying this because it's possible with the vertical auto scaling that I was talking about with the type hints. Oh, okay. I think I'm done. In time? Yeah. Yes, please.
So you said you worked at CVS, right? Which is both, it's got both retail and the PBM side.
Yes.
But you worked, and I actually worked at Caremark, which then became CVS Caremark, right?
Yeah.
No retail space in pharmacy. Could you give a real world example of how either the PBM or the retail pharmacy uses these technologies in either e-prescribing or, some other business fulfillment in the pharmaceutical domain?
Do we use these? I don't know. Streaming is very I think we are still very new to the streaming world. very new. So I don't think we have material use cases at broad level where we use this. Although I do think that these cases can be used in dynamic drug pricing, or they can be used in dynamically ingesting the patient's vitals or something like that, while they are being prescribed some medication, or if there is an app, a CVS app or something, and a patient is coming and they're swiping their card and all, you dynamically get their past data in a streaming fashion, and then apply all these windows and whatever logic you want to tell them the best price for this drug and stuff. So there are applications to it, but honestly, I'm pretty new to CVS, so I haven't faced these issues at scale right now here. But I do think that pricing always has these real-time applications wherever it is.
Insurance checking.
Yes,
Do that, drug interactions.
exactly. Yeah. Thank you. Thanks for the question. And thank